Okay, let's continue our discussion on a Bernoulli equation. So application of the Bernoulli equation, the P plus rho V squared divided by 2 plus gamma Z equal constant along the streamline. So this equation, you should make sure these three different assumption. So steady, here this is not depend on the time, and the inviscidity, the viscosity effect is negligible, and the third is the incompressible. The incompressible is low, the density equal constant. Okay, so you should make sure these three assumption is valid for your case, and then along the streamline, not the different two streamline, this equation always true. The P plus rho V squared divided by 2 plus gamma Z equal constant. So to practically to use this equation, there is a two streamline, and is the point 1 and point 2. Assumption is this pressure P1, P2 is the different, and third, the velocity is also different, and height also different. But in this case, this equation should valid, the Bernoulli equation should valid, so that we can written as like this. Okay, so this is the practical form of the Bernoulli equation. But the thing is, if you investigate this point 3 and point 1 to compare, in that case, this should be not true. Okay, not true, because this is not in a same streamline. Okay, so you should make sure this point 1 and point 3 you cannot use the Bernoulli equation. So here is the application for the freezet. So let's talk about the freezet first. So flow, here there's a reservoir. Okay, so if you fill with the liquid, as you can see, as you like this, and then there is a hole over here at the bottom part. So in this example, as you can see, we can draw the streamline from 1 and 2, right? So because this one is just within the along the streamline, so that we can written as like this. We use the Bernoulli equation, right? Because this is along the streamline. So here at the point 1, because as you already know, the pressure at the one point. It should be same as the atmosphere pressure, right? How about the velocity? Because this is too large reservoir, even though there should be little bit velocity, but it close to the zero. So we assume that V1 equals 0, okay? Because this hole compared to this size of the hole and this reservoir diameter is pretty different. And third, height. The height we should consider. So to consider this height, you need to make a reference line. So in this example, the reference line start from at this point, okay? So you need to consider this height. The Z1 should be H. So that's the reason why, so P1 become P atmosphere, and V1, this one becomes 0, and Z1 equal to H, right? So let's look into the point 2. The point 2. So P2, you should the P2, we don't know the P2, right? So but the thing is, P2, there's a two different way we can measure the pressure. So the first one, consider this height. The second one, because this is open to air, so we assume that pressure is the same as the atmosphere. So which one is true? The first one is the atmosphere, same as the atmosphere. Second one, we should consider gamma Z. So answer for this question is, this should be atmosphere because it is open to air. Okay, so P2 becomes P atmosphere. Okay, how about velocity? Velocity, we don't know that. So let's just keep it as a V2. How about Z2? Because we make the reference line at the point 2, so Z should be 0. This one should be 0. Okay. So, sorry. So here, as you can see, from this equation, we can written as like this, and here the atmosphere pressure is identical, and since the V1 equals 0, so this one should be neglected, and also the height at this point 2, this is same as the reference line, so this one should be neglected. So we can written as gamma H equal rho V squared divided by 2. Okay, so basically the velocity, the equal V2, we can written as 2 lambda H divided by G. Here the lambda is specific weight, so which means that we can written as rho times G, so that we can written as V2 equal E2GH square. Okay, so this one velocity we call the Torricelli equation. The V equal square 2GZ equal to the Torricelli equation. Okay, so another question at this diagram, is how about P3, and how about P4 at this point? So how about P2? Oh, sorry. How about P2 and P4? So I mean this one and this point, and this one and this one. Okay. So this is the across the streamline. So across the streamline. So this is normal, right? So we should use this equation. But the thing is, the radius, the curvature radius becomes to the infinity. So the second term we can remove, so that the p plus gamma z, p plus lambda z, p plus lambda z. So which means that p2 equal p4. So this is very obvious because p4 also open to air. So p2 equal p4 equal p atmosphere. Okay, this is the free Z. The second example is there's a free Z coming from the horizontal direction. The horizontal direction in this direction. So for the horizontal direction, unfortunately, the velocity profile is not uniform. So this is at the point 1, and the point 3 compared to the point 3, compared to the point 1, the point 3, the velocity is much faster. Okay, so you should consider this one as well for solving for application of the Bernoulli equation. So, but the thing is, this diameter compared to this height is very different, which means that the height is much larger than the diameter, so that we usually assume that this velocity profile is almost identical. So we practically, for this case, we use the average velocity at the center line. Okay, so we assume that V1, V3, V2, V average. Okay. And this is also the plus alpha page. So for a sharp edge orifice, the Vena contracta effect occurs. Okay. So the effects is the result of the inability of the fluid to turn the sharp 90-degree corner. So practically at this point we cannot make the streamline like this. Okay, so actual fluid, this time compared to this diameter and this streamline diameter, the free Z diameter is different. So this is called the CC over here. So this CC we call the contraction coefficient. Okay, so contraction coefficient we can written as the area ratio. So first this AJ represent the area of the jet at the Vena contracta, and AH represent the area of the hole. So basically this hole represent AH, and this diameter represent AJ. Okay, so to obtain the more accurate result, you should also consider the contraction coefficient in the real application. So another application of the Bernoulli equation is the confined flow. Okay, so what is the confined flow? So confined flow is a very famous example is the using the syringe like this. Okay, so this liquid is contained in the syringe and there is an opening. So because of the human push this syringe so that the liquid coming from left to the right, right? So this is the confined flow. So in many cases, the fluid is physically constrained within a device so that its pressure cannot be prescribed. And priority was done for the freezer example. Okay, such case include nozzle or pipe of a variable diameter. So which means that this kind of the situation. So nozzle of the pipe with a different diameter. So here and here has a different diameter. The fluid velocity change because the area is different from one section to another. So this is very obvious. This is small and this is big. So if you put one over here, here also mass flow rate should be identical because of the continuity equation. The continuity equation here we called the conservation of the mass. So conservation of the mass in fluid mechanics we call the continuity equation. So for this situation it is necessary to use the concept of the mass conservation. So continuity equation along the Bernoulli equation. So let's derive the continuity equation very simple form together. Since the mass flow rate at the 2 and 1 should be identical, right? So mass flow rate is the kilogram per sec is we call the mass flow rate. And volume flow rate we usually written as volume divided by time. The conservation of mass, which means the conservation of the mass flow rate, the M1 and M2 should be identical, which means that the density times volume flow rate and density times volume flow rate should be identical. So we can written as M1 M2 like rho A1 V1 equal rho A2 V2 because Q equal AV because A represent the area of nozzle. So here area of the nozzle and the V represent the fluid velocity. Okay. So because the density is the identical, so you can written as A1 V1 equal A2 V2 or the Q1 equal Q2. This is called the what? Continuity equation. So basically for the confined flow, you need to use the another concept, very simple concept, use the mass conservation, the continuity equation. So continuity equation, practically you can written as A1 V1 equal A2 V2. Okay. So using this concept, let's solve this example together. Okay. So please stop the video and think about yourself and let's continue. Let's open the let's continue this example. Okay, I assume that you solve this example by yourself and think about yourself and From now on, let's solve this example together. So here, the stream of the refreshing beverage, the diameter is a 0.01 meter. So here 0.01 meter is given. The flow steadily from the color of the diameter equal d equals 0.2. d equals 0.2. Okay. And determine the flow rate, the Q. So actually this should be called the volumetric flow rate, right? The Q unit should be meter cubic divided by sec. From the bottle into the cooler, if the depth of the beverage in the cooler is to remain constant at H equals 0.2. Okay, so H equals 0.2. Okay, you need to supply the Q. Okay, so first I will draw the streamline. Okay, and please check our assumption first. This is steady assumption, steady and incompressible and inviscid. This is our assumption. So also we draw the streamline, so I can written as P1 plus rho V1 squared divided by 2 plus gamma Z1 equal P2 rho V2 squared divided by 2 gamma Z2. Okay. So here, let's see. The P1 and P2 is open to air. So, which means that should be P1 and P2 should be P atmosphere, right? And let's call Z1 equal H and Z2 equal 0 because I made a reference line like this, okay? And third, what we should consider, and we should consider V1 and V2. But the thing is, D, large D and small d, there is only 20 times difference. So the V1 also from now on we should also consider in this example. Okay, so P1 rho V1 square gamma Z1 P2 rho V2 squared divided by 2 gamma Z2 we can written as P atmosphere rho V1 squared divided by 2 gamma H equal P atmosphere plus rho V2 squared divided by 2 plus gamma times 0. Okay, so as you notice that this one can be cancelled out and this one is 0, should be cancelled out. So we can rearrange this equation as a and also here this one is a rho times g, right? So which means that rho also can be cancelled out. So we can written as plus GH equal V2 square. So we got this equation. Okay, let's erase the other information over here. So only we need only we need is this result, right? And this is what we got from the Bernoulli equation. So as you notice that because we want to calculate the v1 and v2, right? There is a two unknown variables, so we need one more equation. So for one more equation, now we try to use the continuity equation. Okay. So for the continuity equation, as I already mentioned, Q1 equal Q2, right? So A1 V1 equal A2 V2. Okay, so here A1, what is the A1? This is the A1, right? And A2 is the, we can written as like this. This is circle and circle. So we know the diameter. So we can written as like this. So if you plug in this result into here, we can written as, sorry, not this is not D1. We can written as like this, right? So this one cancel out, so we can written as a v1 as a function of this term like this, right? We got these two equation. Okay, so now it is time to combine these two results. So if you plug in this result, in the case, we can written as like this, right? So if you a little bit rearrange this equation, we can written as this one as a like this, right? So it is the only left part is we just plug in all the value over here. So here 2, this is gravity, and the h is the 0.2, and 1 minus a small d is this one, and large D is this one. So you can just plug in, and then if you calculate this one, the result should be like this. Okay, so now we know the V2 is the 1.98 meter per second. So here the question is we need to calculate the flow rate, right? So flow rate should be AV, right? So in this case A2 V2, so A2 is this guy, right? So if you plug in, and like this, so this will be our answer. So this result should be 1. So this one, oh, this one should be 1.56 times 10 to the minus 4 cubic meter per second. So this is the answer for the Q. Okay. So this is for the problem 3.7. So let's solve the another example, the 3.8. Okay. So please read this example by yourself, and then after that, if after you think this example by yourself and then come back to this video. Okay. Okay. So here the diagram is given. The air flows steadily from the tank through the holes of the diameter 0.03 meter. Okay, here is the geometry is given. Exit to the atmosphere from the nozzle, so D equal 0.01. Okay, the pressure tank remains the 3 kilopascal. Also, this is the gauge pressure. Okay, that's good information. And the atmospheric condition and the standard temperature and the pressure. Okay, that's good. Determine the Q and determine the pressure in the hose. Okay, let's solve this example together. Okay, let's solve this example together. So since this diagram already is the streamline is given, right? So because we just learned the Bernoulli equation, first we need to use the Bernoulli equation. So first assumption: steady, incompressible, and inviscid flow, right? And in that case, we can use the Bernoulli equation for the point 1, 2, 3, right? So let's apply the Bernoulli equation. P1 plus, so I will quickly written the Bernoulli equation. Like this, right? So as you notice that Z1, Z2, Z3 is same height, so I'm going to remove all the value, okay? And also here P3 open, so pressure should be P atmosphere. The thing is, this one is the gauge pressure, so now I'm going to use all pressure as a gauge value. So this one should be 0, the gauge, right? So this one should be 0. Okay. And what else? Okay. The other information here, this diameter is not given, right? So which means that we can successfully assume that D1, this diameter is much larger than the large D. Okay, so which means that V1 equals 0. So there is no velocity. So this one can be cancelled out. Okay, so this is what we got. So based on this information, in the first sentence, we can written as like this, and the second sentence mean this one, okay? Like this, right? Oh, sorry, this one should be P1. Okay, so this one represents this line. Okay, so we got these two equation. Okay, so for this equation we can, for the V3 we can written as 2p1 divided by rho, right? And from this equation we can written as p2 equal p1 minus rho v2 squared divided by 2. Okay, this is what we got. So here density we should obtain. Here this one is the air, right? So we are going to use the to determine air density with using the ideal gas law. Okay, so ideal gas law, so rho equal P equal rho RT, right? So rho equal P divided by RT. So let me see. We don't. Here the standard temperature and the pressure, which means that the temperature should be 15 degrees Celsius, right? And the pressure should be 101 kilopascal. So pressure we can written as 3 plus 3 represent this one 101. So this should be absolute pressure 10 to the 3 Pascal divided by so gas constant, this one should be given in this problem. So gas constant is 286.9 Newton meter kilogram Kelvin. So sorry, I didn't given in this problem. So this one should be 286.9. Okay, and temperature is 15 plus 273. Okay, so this one should be result is the 1.26 kilogram cubic meter 3. Okay, so this is our density. So based on this information, density is the 1.26 kilogram cubic meter 3. So you can now plug in those values over here, right? So V3 is 2, P1 is gauge pressure, right? 3, 10 to the 3, this is the kilopascal, and the density is the 1.26. So if you calculate this one, the result should be 69.0 meter per second. Okay, so this is the V3. So for the first question is to determine the flow rate. Flow rate is the Q equal AV. So A3 V3. So A3, the diameter is given, square, and 69. Okay. If you calculate this one, the Q should be 0.00542 cubic meter per second. Okay, this will be answer for the A. Okay, this is for the first question. And the second question, what we should calculate? We should calculate the pressure. So pressure for the P2, right? So P2, first we should determine the, when you see this equation, we don't know the V2, right? And we know the P1. P1 is given as 3. So rho we should know. So we should know V2. So V2. So how to calculate the V2? So I will erase this part. Okay. So how to calculate the V2? Since we know the Q is this guy, right? From the first question. So according to the continuity equation, Q2 equal Q3, right? So which means that Q2 is A2 V2 and A3 V3 equal Q3. So A2 we know, since, so we can written as equal Q3, right? So based on this one, we can calculate V2 value. So if you calculate this one, the V2 value should be 7.67 meter per second. Okay. And next step, since we know V2 value, so density we know from here. So only left part is just plug in. So P2, P1 minus rho V2 squared divided by 2. So P1 is given 3, 10 to the 3, and rho 1.26, and V2 is a 7.67 squared divided by 2, right? So if you calculate this guy, in the case, this will be 2963 Pascal. Okay, so this will be answer for the second question. This guy. Okay, so this example also quite easy. Okay, so only difficult part I think is that using the ideal gas law. So for the ideal gas law, this universal gas constant, you don't know that, right? So this one will be given in the actual problem. And also standard temperature and pressure, you don't know that. So for the pressure, it is 101. So actual value is 101,325 Pascal. Okay, but this example, we just assume that 101 kilopascal. And the temperature, we put the 15 degrees Celsius. And other thing is that we just use the Bernoulli equation and the continuity equation. The Bernoulli equation, we already know the continuity equation is Q equal Q, AV equal AV, right? So this one is quite easy, right? So let's stop this session and let's continue our session in the next lecture. Okay, thank you.